Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This video illustrates the calibration of the two cameras in the Tello Talent drone using OpenCV functions. Camera calibration using OpenCV was presented earlier. This tutorial is the application of those procedures for the two cameras on the Tello Talent drone, forward and downward. While there are many basic patterns and fiducial markers that can be used to calibrate the cameras, this demonstration is limited to using the checkerboard patterns. Although a dozen different checkerboard patterns were tested, the demonstration is limited to a single pattern to limit the duration of this video. This checkerboard pattern has 8 inner columns and 5 inner rows. The pattern used in the demonstration has 8 inner columns and 6 inner rows. The two high-level steps are: first, capture the images. Second, use the images to calculate the camera matrix and distortion coefficients. While in practice, many different checkerboard patterns were tested to ensure that the results were aligned for all patterns, only one checkerboard pattern is being demonstrated. There are two ways to capture the images of the checkerboard. One can keep the camera stationary and orient the checkerboard at different angles for the shots. Or one can keep the checkerboard stationary and move the camera to different viewpoints for the shots. The calculations will not be different for either mode of operation. It would be desirable to have a large number of images for refined accuracy in the calculations. For the very limited purposes of this tutorial, approximately 30 images were captured for each of the two cameras on the Tello Talent drone. It is good practice to check for corners in a captured image before saving it for further processing. If no corners are detected in an image, in other words, the connection between the detected corners is not overlaid in the display window of the captured image, then that image will not be useful in calibration calculations. Therefore, it should not be saved any further. The OpenCV package has sample code for the calibration of any camera. There is a slightly older version of the example written in Python. Then there is a more recent version written in C++. Both programs perform the same operations with respect to the initial calculations for the calibration. The C++ program continues further processing by estimating a new camera matrix. It also renders an undistorted image for reference purposes. The calculation assembles a list of points based on input data for the pattern, the number of columns and the number of rows, as well as the square size. Whatever units are used for the square size, the results will be estimated in the same set of units. Here is the checkerboard pattern for collecting the images. It's 8 by 6 by 23. 8 inner corners for columns, 6 inner corners for rows, and the edge is 23. The downward camera is in the center of this image with 2 LEDs on either side. It is a low-resolution infrared camera that captures video in black and white only. As you can see from this example, the images are not bad for our processing work, but it still nevertheless is at a very low resolution, around 320 pixels. The forward camera has a 5 megapixel sensor and therefore captures images at a slightly higher resolution. It has the added benefit of capturing the images in color, although for our calibration purposes, color is basically unnecessary. Here are some sample images that we did capture, and you can compare that it has a slightly better resolution than the downward-looking camera. Here are some sample images that were captured using first the downward-looking camera and then the forward-looking camera. These images were saved as single JPEG files and subsequently used by a separate script to calibrate the camera matrix and the distortion coefficients that we will demonstrate later. Let's go ahead and launch the Python script to collect the images from both cameras. While we have several variations of it, I'll just use the simplest example that I have here and launch it from our PyCharm IDE. Let's take a look at a very simple Python script to capture the images to calibrate the camera. So here is a simple Python script which will use the video stream and present the screens where it can detect the checkerboard squares to the user to be saved as individual images so that it can be run through the calibration program that we will demonstrate later. So it's a very simple Python program. There are some standard libraries that have to be imported. And if I scroll down here, the key parameters for running the script is, first of all, the source of the camera. Is it the forward-looking camera or is it the infrared downward-looking camera? We let the script know that. Then how many innermost squares are there in the horizontal direction or column-wise, and how many innermost squares in the vertical or rows there are. I've also specified here as a parameter the edge width of the squares. Although this is not used in the calculations, it will come in handy when we do the calibration work, so I thought it best to preserve it with the data that we are capturing here. The initial commands to get the Tello cameras working, first of all, we have to set the command itself in UDP mode, and then we turn on the streaming function of the Tello drone with the stream on command, and thirdly, we tell it which camera to use. In this case, it's down vision 1, which means use the downward looking camera. If it had said down vision 0, it would use the streaming from the forward-looking camera. So once that's out of the way, then we check, and this is where the square size that I mentioned comes in handy. This is the only place where it comes in handy. Rest of the things are purely to preserve the folder naming convention that I will show you a little later. So once we've got all that out of the way, then, and we have some warm-up or delay for the streaming to start, we let the OpenCV function video capture know where the video source is going to come from. It's UDP at broadcast, and the port number is there. And OpenCV will take care of processing that video frame by frame. So once we've done that, we read the first frame in here, and we check to see whether it read anything properly or not. So the camera status has to be true. And then my camera frame current will have some image in there. We immediately show that frame to the user through the IAMShow command in the window named capture frame, but we resize it to 640 by 480 just purely for presentation purposes. Obviously, when we are doing checkerboard corner detection, there is no need to worry about color. So we convert the image to grayscale in this command in here, and we are going to use the grayscale image for our processing. OpenCV has a function called find chessboard corners to detect the inboard corners, and we go ahead and use that. And we have to, of course, tell it how many innermost corners there are in both the vertical and the horizontal direction. Once the checkerboard corners have been found, in other words, the system finds it, we draw the checkerboard corners with the default settings. In other words, there's no fancy coloring of the first innermost corner, second innermost corner that is traditionally done in most demos. Here I just settled for a single color, and I just draw the corners and have the circles illustrate. We show the detected corners in a different window, and that window is called detected inner corners. At this stage, we let the user decide whether they want to save that image or not for the calibration work, and so the system waits indefinitely until a key is pressed. If the spacebar key is pressed, then it will go ahead and save that image through this simple code here, and it writes it to the disk in the settings that are provided. If it saves it, it'll also present that same image as a saved image window minus the connected squares. If no corners are detected, then a separate window is displayed called no inner corners, and then we wait to refresh for the next frame indefinitely, and the user can present any key. At that stage, it goes to the outer loop, and at that loop, if the user wants to exit, then they can press the letter Q and exit, or press any other key to continue processing the next frame. In essence, this is a very simple program that will just show you what has been detected or not detected, and then while it's waiting for you to change the orientation for the next key, you can move the camera or the board a little bit so that you get different views. I've collected approximately 30 frames per checkerboard, and there are lots of checkerboards that I have, but I'm not going to go ahead and show you all of them in this demonstration right away. We're going to stick to the 8x6 23 millimeter wide demonstration. So let us go ahead and run this script, and I'll just do it the simple way. So here is the close-up view of the captured frame in color by the forward-looking camera. And here is the view of the detected inner corners at a much closer look, with the corners being connected by lines and the corners themselves indicated by circles. Here are the two folders that retained the images saved during the acquisition of the images. So the Tello 8x6_23 represents the views from the forward-looking camera, and the other folder, down x86_23, represents the views, the images from the downward-looking camera. So let me cycle through the images on the downward-looking camera. As you can realize immediately, it is of a much lower quality than the forward-looking camera. So let's go ahead and take a look at the similar set of images for the forward-looking camera. The improved quality of these images should be readily apparent, as well as recognition that these images are in color, although the subject is really black and white with a white background. So hopefully this gives you an idea of how very quickly, in a quick and dirty method, the images can be acquired by using a simple Python script. So let's move on now how to use these images for the calibration of the camera lenses for both the forward camera and the downward looking camera. Let us take a look at the Python script to calibrate the camera using images that were recorded previously. So in this routine here, we will use a checkerboard pattern, 8x6 with 23 millimeter edge, a pattern of known size. We'll use the images that were captured previously. We will find the chessboard corners to find the inner corners of the pattern, and then we will ask OpenCV to perform the camera calibration. So as I scroll down here, we have the standard import functions. We're specifying the number of inner columns and number of inner rows. We specify the iteration criteria here, and this may require, in your case, some tweaking, but generally I've seen that if you have clean and clear images, it converges fairly quickly. And you may be familiar from the previous section in our presentation We already have the files saved in a dedicated folder. This folder is for the forward-looking camera 8x6 with 23mm edge. We go through each of the images one by one, convert it from color to grayscale, find the chessboard corners, and if we do find the corners, we obtain the coordinates and draw the corners for the confirmation by the user. Once that's done, we are collecting the points in an array, and we will use that for the calibration camera. So after we've shown the user what we've collected, we close out all the windows and then perform a very simple calibrate camera function that is available in OpenCV with the points that we have found and the images to create the camera matrix coefficient and the distortion coefficient. So let's go ahead and run this program and show you what the operations look like, and then we will look at the actual output with respect to the camera matrix and the distortion coefficients. So I'll go ahead and now run the script, and since everything is pre-programmed and set up, you can see the windows that detect the corners all show up one by one. All the files will be displayed, and at the end of the iteration they'll all be dismissed and the camera output will be presented on the screen here. So now you see, once the run is complete, it presents the camera matrix and the distortion coefficients. So here in the output window, you can see that the camera matrix and the focal length is specified, and also the distortion coefficient was calculated. The data is written to a file so that it can be used later on, and then we also perform some inverse undistortion calculations to show you what the results look like. But I deliberately saved the data, the camera matrix and the distortion coefficient, in two different files so that we can use it whenever we like for whatever purpose we need these data for. So let's run the script again, but this time we will use the images acquired by the downward looking camera. So we need to change the name of the folder here, and that's what I'm doing. And now we can run the script with the new folder name. We use the traditional run method to run the script. And as you can see, it's a slightly smaller window because it's the smaller image from the downward looking camera. And it goes through essentially the same set of steps. And in all cases, it has identified the inner columns and the inner rows. Now it's dismissed it, and it's going to go ahead and create the matrix. And you can see from the window here that the focal length and the center point for the camera are slightly different. The focal length, because it's a very, very small camera, is pretty much right spot on, exactly the same value in X and Y, but the center is slightly off. And then, of course, we have the distortion coefficients. So we will use these values later on in future tutorials, not right away. But I thought I'd set this aside and get the work done, and then we can start focusing on basic OpenCV principles before we start migrating to more important topics using the Tello EDU, OpenCV, and autonomous tracking. This video tutorial is an extension to an earlier demonstration on camera calibration using OpenCV. The Tello Talent drone has two cameras which were both part of this demonstration. The processing was performed using two Python scripts. First, to capture a set of images from a camera. Second, use the images to perform the calculations to estimate the camera matrix and the distortion coefficients. That's all, folks. Thanks for taking the time to view this presentation. Would love to hear from you with your feedback. You are always welcome to be critical in any which way you can. Until next time, bye for now. This presentation was prepared with assistance from OpenCV for the image capture and camera calibration programs, and from free open source software for the two integrated development environments, IDE, from PyCharm for Python and KDevelop for C++. Also, the backbone for the preparation of this video is from Inkscape, OBS Studio, Kdenlive, LibreOffice, and of course, Ubuntu. Family, teachers, viewers, and peers provided valuable feedback. My apologies if I have inadvertently omitted anyone from this acknowledgement. A very big thank you to all for the assistance.